All right, we talked yesterday about how proportional relationships are special examples of linear relationships or linear equations. So we're going to continue with that idea today, and we're going to compare proportional relationships. Proportional relationships. Now, when you're doing these problems, and just like yesterday in section 4.9, we are going to be doing some of your assignment as part of the notes. So we're going to start with problem number 1. So please make sure that you're showing all your work and all your thinking, and please make sure you follow all of the instructions. Each part of these problems, they're designed to help you put some connections together, help you think about the problems the right way. So if you follow along, you should be in really good shape, and it should really increase your understanding of how these proportional relationships work and how they relate to linear equations. So let's take a look at this example right here. It says on number 1, two friends, Emily and Jake, went on separate trips. Emily drove 210 miles in 6 hours. The graph shows the distance and the time of Jake's drive. So this information right here, so I'm going to circle this. This is Emily, and I'm going to circle this. This is Jake's drive. So this is the information we have about Emily's drive, and this is the information we have about Jake's drive. And then the question here is, who's going faster? Well, when they talk about who's going faster, they're talking about a rate. Okay, so let's do Emily. So I'm just going to put Emily here. She drives 210 miles in 6 hours. And then I'm going to put Jake over here. Jake, he drives, well, let's see, how could we figure out what his rate is on this one? You'll notice that this is a nice straight line. Well, if you were paying attention in the last unit or the last section, remember when we say rate, rate is the same thing as somebody talking about the slope on a graph. So we could find the slope right here a couple of different ways. We could find a few convenient points, pick any one of those you want, and we would go up and over. So this would be up from 80 to 120, so that would be up 40. And this would be over from 2 hours to 3 hours, so that would be 1. So his is 40 miles in 1 hour. Now, I'm not done with Emily yet, because remember, they're going to ask us who's going faster here, and we've got to figure that out. And it also says by how much. So I do want to point out one more thing about this. Because this is a line that goes through the origin, then this point right here would be the unit rate. So this is 1 comma 40. That right there is the unit rate. Okay, so if we have a graph like this, you can immediately tell what the rate is, what the slope is, what the unit rate is, just by looking at that. So here's the answer for this one. So this is Jake. He's going 40 miles per hour. But again, we normally don't talk this way, 210 miles in 6 hours. So we're going to grab the calculator really quickly. So I've gone ahead and thrown this into the calculator. I did 210 divided by 6, and I ended up with 35. So this is 35 miles per hour. Okay, so it says who's going faster? Well, it looks like in this particular case, Jake is going faster. Okay, and we've got our work to show that Jake is going faster. And then it says by how much? Well, that means we need to compare the two of these. So we're going to say he's going faster by 40 minus 35 by 5 miles per hour. Okay. And then it says write an equation for Emily's drive and an equation for Jake's drive. Well, let's do Jake's drive first, because that's a little bit easier. We've already identified what the slope is, and we can look at this and we can tell what the y-intercept is. Now again, because this is proportional, no surprise that the y-intercept is 0, so I'm going to put a b of 0. And then the slope again is the same as the rate, which we already found. So the slope on this one is 40. So this would be for Jake, y equals, this would be 40x plus 0, or just y equals 40x. So I'm going to put a circle around that. And again, we always want to remind people on this, because these variables can represent lots of different things. X in this particular case represents hours, and y represents miles. So we always want to include that. Now, we don't have a graph for Emily, but we can still figure that out. Remember, this is her rate, and we'll assume that she drives the same speed the entire time. So if that's her rate, and this is proportional, then she would have started out in her driveway 0 hours, 0 miles. So it would have gone through the origin. So on that particular one, 0, 0, started out in 0 hours, and 0 miles. So that means her y-intercept would be 0, and then this would be her rate. So for Emily, it's going to be y equals 35x plus 0, because remember that would be the y-intercept. So we're going to write down y equals 35x. We're going to circle that, and we're going to say the same thing on this one as we did on the previous one. Again, we're going to tell everybody what these variables represent. X represents hours and Y represents miles. Now, in the future, if you want to just write down the equations, circle those, and then tell everybody just once what X and Y represent, then that's totally okay. All right, so let's take a look at the next one. It says the equation represents the rate at which Daniel ate chocolates. Okay, so rate, again, think slope here, and x equals days and y equals chocolates. And the graph shows how many chocolates Clay ate over the course of 5 days. So you'll notice that we've got this nice graph over here. It's got this nice straight line that happens to go through the origin. Remember, that tells us a whole bunch. And then it says, what is their daily rate of eating chocolates? So I'm going to do the same thing here. I'm going to do Daniel in red, and I'm going to do Clay in blue. So for Daniel, we've got an equation. Now, that equation is written as y equals mx plus b. There is no y-intercept there, so that kind of confirms that this is a proportional relationship for us. So we're going to write down that his rate was 4 over 1. Now, remember, the y's are the numbers that go on the top, so that would be chocolates, and x's go on the bottom when we're calculating rate or calculating slope. So this is going to be chocolates per day. Okay, so we're going to circle that one. And then over here, again, let's find the easiest one that we can on this. Let's just find this point right here. This is 1 day and 5 chocolates. So if we were to put the calculated rate of change here, calculated slope, this is up 5 chocolates and over 1 day. So this is going to be 5 chocolates in 1 day. So those are the two rates. All right. Write an equation for Clay's chocolate eating. We already have Daniel's chocolate eating. Okay, that's right here, and it tells us what these are. So I'm just going to circle that so we know we've got the equation for Daniel. Clay is going to be the same type of thing. He's just going to have a different rate. So he starts out at 0, 0. So that would be a y-intercept. I need to change colors here. That would be a y-intercept of 0. And a rate or a slope of 5. So that means this would be y equals 5x plus 0, or that's just going to be y equals 5x. And I'm going to circle that, and I'm going to point to this guy right here so everybody knows that x is the number of days and y is the number of chocolates. And then it says, how many chocolates would each one eat in 8 days? So let's think about this. This graph isn't big enough to just kind of follow this out and pick the point from the graph. So we're going to use the equation on both of these. So remember, this is y equals 4x for Daniel, and the other one is y equals 5x for Clay. So if we want to know how many they can eat in 8 days, what that means is, and I'm going to put this in black, x equals 8 days. Notice that this is kind of helpful that we labeled this up above, or that they gave it to us. So x is the number of days. So if they told us how many days we had, we could plug that in and we could figure out how many chocolates they're going to eat. But by the same token, if they said, hey, how long does it take them to eat this many chocolates? That would be the y, and then we could solve the equation for the x. So keep that in mind. You may run into a couple of those. So here's what we're going to do. We're going to do y equals 4 times 8. So that's going to be y equals 32, and I'm going to say 32 chocolates for Daniel. And changing colors again, this is going to be y equals 5 times 8, so that's going to be 40. So that's going to be 40 chocolates for Clay. And those are the only questions there. They're just asking us to kind of investigate this situation right here. So let's take a look at number 3. It says, 2 students measured the speed of their pet snails. I guess some people have pet snails. One student took measurement for snail 1 and put the data in a table. So we've got some numeric data right here. While the other student took measurements for snail number 2 and created a graph. So we've got the graph for snail 2, some graphic information here. Their findings are shown, and it says, find the speed of each snail. Now, we're going to assume that these are proportional relationships, but we are going to do a little bit of double checking. On snail number 2, it's easy to tell that this is proportional because it starts at the origin and then we've got a straight line. So that one's definitely proportional. We can just find one of these rates of change or one of these slopes and it'll tell us what the speed is of the snail. For this other one, we might want to double check and make sure that this pattern works out. Notice that we're going up 1 minute. Every one of these x coordinates right here, every one of these minute changes here. And then the centimeters go from 0.3 to 0.6 to 0.9 to 0.12 to 1.5, 1.2 and 1.5. So if we were to calculate a rate of change, we would do 0.6 minus 0.3 over 2 minus 1. So we get 0.3 over 1, and that would be centimeters per minute. Okay, if we did it down here, 1.2 minus 0.9. So if we did this one, we have to do that one, 4 minus 3. So that's a 1 on the bottom, and that is a 0.3. So we get the same answer here. So the speed of each snail. So on snail number 1, this is going to be 0.3 centimeters per minute. Okay, so I'm going to circle that one. And then for snail number 2, let's find where we are right here. So if this is 2 minutes, 1 minute has to be right here. Okay, so we'd be about right there. So that is in between. Let's see, if this is 0.2 and this is 0.4, this would be 0.3. And it's not quite at 0.3. So because we've got a graph, I think our best thing to do here would be to just estimate. So I think that's about 0.25. Okay, so I'm going to say that that's 0.25. So 0.25 centimeters per minute. Okay, so I'm going to circle that. Now, there is one way that we can kind of double check that our guess is correct. So if this is 0.25, or think of that as 25 cents for 1 minute, for 2 minutes, it should be 50, so 0.50. So let's follow this up and notice that that matches up perfectly there. Nice convenient point. That would be kind of like doing this, rising 0.5 and then a run of 2 minutes, and then we divide. So I think we've got the answer perfect. If it didn't work out perfectly in a situation, as long as you were pretty close, then I think that would be just fine. It says write an equation for each snail. So remember, the y-intercept for both of these is going to be 0. So this is going to be y equals 0.3x plus 0. So this is going to be y equals 0.3x. So I'm going to circle that one. And then on this one, we're going to have y equals 0.25x. And then remember, it goes through the origin, so that would be 0. So if you can immediately write it as these two answers, that would be totally okay. We do want to make sure that we say what each one of those variables represents. So the x-axis is minutes and the y-axis is centimeters. So here's like the x and here's like the y. So x is like minutes, y is like centimeters. Let's make sure that this matches up over here. This would be like the x and this would be like the y. So it's the same thing for each one of them, as it should be. So x equals minutes and y equals centimeters. So we've given a complete answer for that one right there. We wrote the equation and we told everybody what the variables represent. And then it says which snail is faster. Well, it looks like on this particular one, because this snail, snail number 1, can cover 0.3 centimeters per minute. Gosh, that is really slow. And the other one can only cover 1/4 of a centimeter per minute. Snail number 1 is faster. So let's go ahead and write that down. So snail 1. And I'm going to write 0.3 cm per minute versus the other one, which would be 0.25 cm per minute. And then everybody can tell that this one right here, that's the biggest one. Okay? Now, it says are all of these proportional relationships. So let's take a look at these. Every single one of these is a proportional relationship. You can tell based on the graph that every one of the ones where we had a graph, those are proportional. And you can also tell because they have the same rate. And if we stop this guy at the starting line, we would have the point 0, 0. He couldn't go anywhere if we didn't give him any time to do that. Okay? On this one right here, you can also tell that this would be a straight line. And it would start out at 0, 0, just like the other one did. We had this line right here, and then we also, based on our assumption that if she was in her driveway, she wouldn't have gone anywhere if we didn't give her any time. Every single one of these is proportional. So we're going to circle a big fat yes on this one. And then it says, how can you tell? Well, by looking at a graph, we can tell really quickly. They are all straight lines. straight lines, and they all go through the origin. Okay. Now, this means that proportional equations are just special type of linear equations, as we've been talking about the last couple of days. They all have a y-intercept of 0. So the fact that they're straight lines, they all have this, the rate of change is always the same and stuff like that. That's the part that makes them straight lines. And the fact that they go through the origin, that's what makes them proportional. That's what makes that 1 comma whatever that point is, like we had right here. That's what makes that. So that's the unit rate or the slope. Now I hope you notice something about every single one of these equations. So let me blow that up just a little bit so we can see what's going on here. Look at every one of the equations. Y equals 35x, y equals 40x, y equals 4x, y equals 5x. Let's see, and on this one, y equals 0.3x and y equals 0.25x. So whenever we have a proportional relationship, it's always going to look like this. And because it's proportional, we give it a special letter. So I'm going to put a k right here. Okay, k is the unit rate. So it's also the slope. We could use an m there, but by convention we normally put a k right there. Remember, letters at the beginning of the alphabet are usually representing constants. So k is the unit rate. We could also call it the constant of proportionality. Okay, and maybe because we use c for other things, they chose k for constant or something like that. So I'm going to write constant of proportionality. Proportionality. Now that is a mouthful. I don't blame you if that's a bit of a struggle. I'm not a huge fan of that word there. I kind of like to call them scale factors and things like that. But as long as you know that that's the slope of the line, that's the unit rate, then you're in really good shape. I do want to make you aware that there are times where you'll see somebody else refer to this as something different. Some people call this direct variation, because all we have to do is kind of like our chocolate example. You tell us how many days they have and we'll tell you how many chocolates they can eat. They're directly proportional. So we call that direct variation. Okay. All right, you've got the rest of the assignment to do. There are problems that are very similar to this. I think we've prepared you very well. If you've got questions, please ask, but good luck.